Next up, want to predict the hybridization of the oxygen atom in water and draw a picture of its three-dimensional structure. And lastly, explain why its bond angle is 104.5. Okay, so before we can get into the electronic or molecular structure, as usual, begin with the valence electron, so the Lewis structure first. And we will have 6 electrons coming from the oxygen plus 2 by 1 due to the hydrogen, and that's going to give us, again, 8 electrons to mess around with. We're going to place oxygen as our central atom because hydrogen can't be it, and just begin with 1 bond to each of the hydrogens. From there, we'll have 4 electrons in the bonding pairs, and the only place the other 4 can go is going to be on the oxygen, so let's go ahead and place them. All of our electrons are now taken care of. Let's double check on our formal charge. On each of the hydrogens, we are going to have 1 minus 1, yielding a 0. On the oxygen, we will have 6 minus 4 minus 2, yielding 0, 2. This is exactly what we had expected, and so this is the correct Lewis structure. So as usual now, we begin by counting the steric number in order to determine its electron geometry. And that is going to be the number of atoms attached to it plus the number of lone pairs. And so we'll have 2 bonding pairs because of the 2 hydrogens and 2 lone pairs because of the 2 lone pairs. And so that's going to give us a steric number of 4. But in its notation, let's account for the fact that 2 are bonding pairs and 2 are lone pairs. So that is going to be AX2, E2. So this is our bonding pairs and this is our lone pairs. Okay, so now that we have this, we can pull up the chart and we come down to the total domains, so that should be a steric number 4, and then we begin accounting for the number of lone pairs. And so our electron geometry will just tell us that the steric number is 4, and so that will tell us that it is tetrahedral. But our molecular geometry will account for which ones are bonding pairs and which ones are lone pairs, and that is going to be bent. And so now what that means is that we can just go and check what hybridization it is for steric number 4, and that's going to be sp3. A good way to remember this is that, okay, so first off, we have 1 s orbital per level, 3 p's, 5 d's, 7 f's. Each orbital can take 2 electrons. A good way to remember is just count the number of orbitals that you have. So 1 plus 3 is going to give us 4, and so that's going to represent a steric number of 4. Let's say we wanted to represent a steric number of 6 for whatever reason, then that would be sp3. So currently we have 4, and then we need to add 2d in order to get to 6. And so that's a quick way to just remember it just off of the steric number. And so our hybridization is going to be sp3. Okay, and then let's go about drawing that. You need to remember that all of these drawings here and where they have decided to place the lone pair is based off of the optimal structure that would minimize the electron-electron repulsion. And so it'd be best in our scenario to have our molecule in this configuration, which is 1 here, 1 here, and then we have these 2 groups for our lone pairs. And so let's just redraw that and we just like turn it over so you can think about it. And so we have O and our 2 H's that are in the plane, and then those 2. Yeah, and so what's going to happen is if it was tetrahedral, so let's say OH4 for whatever reason, then what would happen is we'd have a bond angle of 109.5 between everything. But then because of the fact that these 2 are now instead going to be electrons, so lone pairs, the lone pair of electrons are going to cause an extra push compared to the electrons in the bonding pairs. And so the electron isn't going to be as balanced out in terms of the repulsion forces. And so that's going to cause these angles to be bigger than they were supposed to be. And what that is going to mean is that the angle between the two hydrogens is going to be less than the idealized 109.5 degrees. And so usually in the question given, you can just leave it as less than 109.5. We are told that its bond angle is 104.5. That still makes sense because that is still less than the idealized 109.5, and that is caused by the fact that you have two lone pairs of electrons. Okay, next up, we would like to explain the electrostatic potential map for water and see how it corresponds with what we've been given here. And so in this map, in this map, we have it looking basically a bit like that. And then we have our actual structure in here. And so we need to understand how to read this. And so what the red means is that you have an area of high electron potential. So that just means that the area is going to be a little bit more negative because you have more electrons around it. And our blue means that we have a low electron potential. And so we can obviously explain this as being caused by not only the fact that oxygen, so A, we have the fact that oxygen is very much so more electronegative than the hydrogens. And so what that is going to mean is that in our bond, so let's take just one bond between the oxygen and the hydrogen, we're going to have the electrons more towards this side than the hydrogen because the oxygen has more pull on them. And so what that is going to mean is that the oxygen is going to gain a partial negative charge and the hydrogen is going to be left with a partial positive charge, and that's just because of the unequal distribution of electrons that's affecting them. And so oxygen will have a very high electron potential around it because it's almost taken the one electron from this hydrogen and the one electron from this hydrogen. Additionally, we have the fact that there are two lone pairs of electrons around the oxygen, and so that's going to increase its electron potential too. And so that explains why this area is going to be red due to those two factors. And the region around the hydrogens is going to be having a low electron potential because the electrons are simply closer to the oxygen due to its electronegativity. And so this will explain both the red and the blue. This just explains why it's that red compared to that of nitrogen. Because nitrogen also has a higher electron potential, a higher electronegativity than hydrogen. And you can see that that's causing it to be slightly red due to these partial charges that we've talked about. But we can see it's not as red as it is in this scenario, and that's just because of those lone pairs of electrons. And that's it for this question.